Hello, friends and scholars, and that would be two of the same. So, hello. I want to use this opportunity to introduce logarithms to you, which corresponds to skill 20 on haiku. So, as you know what you need to do. You need to have some paper for notes, and you don't really need scratch paper for your tries, but actually, you could just put them into what you're doing for notes. But you will need some scratch paper so you can work out your IP problems. And then you'll definitely want to have a calculator. It needs to be scientific because you need to have the buttons log for log and ln for natural log. All right. And of course, positive attitude. We always want to have that. So we've talked about exponential functions. Functions look like y equals a times b to the x. We're going to specifically focus on the case where a is 1, so really just y equals b to the x. So our initial value is just 1. We're also going to look at that number e that we saw in previous lessons. We use that with our continuous compound interest. Technically, it was designed by a guy named Euler. Looks like Euler, but it's Euler. So we're going to look at the E and how that relates to all of what we're doing. And then you also need to understand decay versus growth. Okay, so we saw decay happen when B was between 0 and 1, and growth happened when B was greater than 1. Okay? All right, so today's lesson, we're going to know what a logarithm is in terms of its exponential. We're going to evaluate simple logarithmic expressions, and then we're going to talk about special cases of the logarithm. Okay, those are going to be what we call the common log, and the natural log. Okay, so we'll talk about what those mean momentarily. Before we do that, let's start with what a logarithm is. Okay, so when we have a logarithm with base b, okay, and what we have to say about that is that b has to be greater than 0, but it cannot equal 1. Okay, it has to be greater than 0 so that we have either a decay or a growth factor, but it can't be 1 because 1 is neither decay nor growth. Think about it this way. If I had y equals 1 to the x, well, 1 to the first is 1, 1 to the second is 1, 1 to the 1 millionth is 1. So that it just doesn't make sense to have b equals 1. Okay, and the way we write this is y equals log base b of some argument a. Okay, and so we'd write this as the function y equals log base b of x, so x just being the argument here, if and only if b to the y power equals x. Now, let's make some connections here, okay? This can be really weird to look at, but just, oops, sorry about that. Just know that this little base b in the log is telling us the base number, the big number of an exponential. Okay, what a log is equal to is always the exponent in the exponential form. And then this x in the logarithm is an argument, and it's what an exponential equals. Okay? So that means that logarithmic functions are actually another way to undo exponentials. Okay, so logarithms undo exponentials, okay? So let's practice writing some writing exponentials from these, okay? So remember y equals log base b of some argument, okay? So in this case, I look at my subscript on the log, and that tells me the base of my exponential, okay? Because we know that the log is equal to 3, that becomes the exponent. You know what? Maybe I should color code this. Okay, so what my log equals is the exponent of the exponential. And then the argument on here, let me use a different color. Let's use green. The argument on the log is what the exponential equals. Okay, so just those pieces in that order is how we're going to figure this out. So let's try another example. This one, I have a base of 7. I have an exponent that's going to be 2, and 7 squared is indeed 49. On the next one, I have a base of 2. My exponent's going to be -4, and I'm claiming that that's 1/16. Now let's review what we know about negative exponents. Okay, 2 to the -4 is the same thing as saying 1 over 2 to the 4th. And 2 to the 4th is just 16. Okay, so that's why that works out that way. Okay? So why don't you try these on your own? I'll pause the video and then I'll put the answers and I want you to try them out. Okay, the first one you should have, had 2 to the 5th equals 32. Second one you should have 3 to the 6th equals 729. Okay, so evaluating logarithms. Okay, so some steps that'll help you out. The first step would be to convert to exponential. Oops. Okay, so after you convert to an exponential, then what you're going to do is you're going to ask yourself, base to what exponent gives me the argument value. And then finally, the last step to be aware of is, watch for common logs. So watch for log versus natural log. Now this log is the log that has no base number written. So nothing is written here. That's going to be your common log. And we'll talk about that in a moment. And then your natural log is going to be, again, we'll talk about this in a moment, but it's going to be the one that involves that Euler's number E. Okay? So if I'm looking at this, first thing I'm going to do is pretend that this is equal to y. And so then I can write this as 4 to the y equals 64. Well, you can ask yourself, okay, well, what multiplied to itself, 4 multiplied to itself how many times will give me 64? Well, that would be 3 times. Okay, so the value of this logarithm is 3. And if you wanted to test it out, you could do this on your calculator. Log 64 divided by log 4. Okay, and I'll talk more about that in a moment, but there's a log button on your calculator that you could use that would help you to do this, and it should give you 4. If I look at the next one, again, think of this as 9 to what power equals 1? Well, what exponent do you have to have in order for a base to that exponent to equal 1? Well, let's put it in on a calculator. So log 1 divided by log 9. I hope you got 0 on your calculator because that's what it is. The next one is saying 5 to what power, the power of y, equals square root of 5. Well, for this one, it might not be so obvious. I mean, you could do log square root of 5 divided by log 5. Notice that I'm closing my parentheses here and here. You could do this on your calculator. Your calculator is going to give you 1/2. Why in the world would an exponent of 1/2 give us a square root? Well, you may remember I talked about this in the past. If you have a, by the way, y is a half. If you have a fraction exponent, okay, I always use the analogy flower power, okay? And when I do that, I think of this flower growing out of a ground where the roots hold the flower into the ground, so the denominator is a root, and the numerator is the power. Okay, so this would be, if I wrote this out, a square root. So a root of 2 is a square root of 5, and then it has a power of 1. So that's why that works. Okay? So try these out on your own. I'll pause the video and then see if you get the values. Okay, hopefully you got these answers. Sorry that the answers are so far away from the problem, but first one, this is true because 3 to the third makes 27. So that 3 had to be the value. Next one, 25 to the 1/2 is equal to 5. And remember, we know that because the 25 to 1/2 means square root of 25. And then the last one, 7 to the third is 343, which is why this was equal to 3. Okay. All right, so a couple special cases. Case 1 is going to be the common logarithm. Okay, and that assumes a base of 10. So if you see log 1,000, that's the same as saying log base 10 of 1,000. So that would have to equal 3. Okay, because 10 to the third is 1,000. This next one, log 0.1. I would prefer to have thought of that as log of 0.1. But again, that's saying 10 to what exponent equals 0.1? Well, 0.1 is 1/10, which is 1 over 10 to the first power, which we'd write as 10 to the -1. So this should equal -1. Okay. The next one is the natural log. And it's written, it looks like IN, but it's LN, okay? That's LN. But we just write it like that. Okay, it uses E as the base. So if I see natural log of 50, that's saying E to what power equals 50? I don't know what that is, so I'm going to use the calculator. Okay, you should see a calculator or a button on your calculator that says LN. Okay, so LN 50. And that says that we would have about 3.912. All right. And you can find these buttons on your calculator. Please note that when you're looking at the log button, you might see 10 to the x above it. That's because 10 to the x is an inverse to log. And if I have the natural log, like right here, e to the x is, so e is the inverse of the natural log. Okay? So those are inverse pairs. Otherwise, we would just say, like, if I had 3 to the x, its inverse would be log base 3. If I had, let's say, 12 to the x, to undo that, we'd have log base 12. Okay? So these two are buttons that you can use your calculator for. If you were trying to figure out, like, log base 7 of 23, and you couldn't do that, the way we would do this is we'd write it as log of the argument divided by the log of the base. Okay. And so we could do that in our calculator just like we did a few times already. So we have log 23 divided by log 7. And that gives us about 1.611. Okay. All right, so that's all we have in this lesson. So try these out on the IP Google form, and then we will we'll go from there. So thank you.